about here, unrelated to programming languages. But yeah, our Raspberry Pi is running this server here called Octoprint. And it's called Octopi is the project for Raspberry Pi. So this guy allows me to upload stuff from my local computer. So I can say upload, pick a file from here, upload it, it puts it onto the local hard drive, local flash storage on the printer. And then I can print it directly from here. And you can keep track, you can monitor this thing. So if I look at temperature, the current thing's printing at 200 degrees at a 50-degree heat bed. You can actually view the G code, see all the things that it'll take a second to pop this up. So that's, so this is showing the current layer. But you can also do time-lapse videos where it automatically, every single time the Z-axis changes, it takes a picture and then shows you a video over time. So I can show you an example of a video. It's not impressive looking right now because our camera isn't centered right. We're printing a camera mount currently where this thing is literally taped to the side of the thing.
I like the picture. It's just
Yeah. So what the mount is going to mount it actually to the Z-axis, the print bed. So as the print bed goes up and down, the camera travels right with it. So it'll have a good picture of it. But just to give you an idea of what this thing looks like, you can kind of see that eventually it does come into the thing a little bit. There, you saw the but I promise you that if you had that centered, you would have seen the thing, become a real object.
So is this connected via like a USB directly to the Pi then?
Yes. And what we're going to try to do is have that single Octoprint work for all of the printers with like a USB hub. Yeah. So you can actually have a single server to go in and start a print. Okay. And then we're going to have also a surveillance thing with Octoprint. Well, probably not Octoprint. Even though we do have cameras like this, we're probably going to do it with a secondary Pi. Yeah. Possibly out the same one because we do have the 4th gen Pi that has a quad core. Right. But where you have cameras pointing at each of the printers, so you can see what's busy and what's not, and then you go into the print server and select a printer that's not currently busy, that has an empty bed, and print to it. So you can do that from anywhere on campus, and then just go down and pick up your print when you're done. Wouldn't that be cool? Yeah. So we're investing quite a bit in makerspace to make it right. What's this? Yeah. Yeah, but anyways, this Octoprint thing is pretty slick. What's really nice is you can just do this type of thing just to see what's happening, because what happens otherwise is I have to beam in.
Wait.
So if I'm at home and I want to check on my prints.
Oh. Pretty fun, actually. Yeah.
What happened? Did it crash? Take over. Oh, see, I bet you maybe it's because of the screen capture or this thing. It must use the same protocol, the beam, and maybe the screen record for because I'm not able to connect to the beam here. We'll try again. That's how I usually test them. I can do it from my phone though. So I just drive the telepresence robot around and just look at the printers to make sure it's still going, make sure I don't see a nest of stuff. So that's how the cool kids 3D print. This is what it comes down to. All right. What class is this?
470.
We do Dr. Racket?
Yeah.
All right, for today we had our question. That's right. Repeat was last time? Mm-hmm. Okay. Yeah, so there seemed to be, I want to talk about a couple of things here. Hopefully I saved this. Is this us?
Hey, that looks good.
Okay. Yeah, because we have this new version of Mac OS that's supposed to have all these problems and destroy everything, so I decided to install it. So far it seems to work okay.
Did you hear about the Wallace issue with it?
Uh-uh.
He recorded an hour lecture.
Oh, yeah, but I'm not, is that related to this? I knew he had a problem recording. I didn't know it was real.
Because of the Catalan update.
Nah, it seems like maybe he's just finding something to blame.
Maybe.
He probably forgot to hit record. Actually, probably the real problem is he's using Panopto. Yeah, because we're on campus, we're supposed to officially use Panopto for all of our recordings because that's our officially supported.
But you decided to use something that actually works.
Correct. Yeah, technically it's very off limits. Yeah, what I do is like more than frowned upon. By putting stuff up on YouTube, yeah, we're not supposed to do that.
Really?
Yeah, but it works. If you need to view the video, it's on YouTube and it works. Very rarely do I have screen captures fail. Let's watch it fail like right now.
Maybe it is Catalina.
Yeah, so I'd rather have something that works and have somebody say, well, you really should be using the tool that we have on campus that doesn't work. And then I say no. All right, so let's talk about some of the challenges that folks had with the assignment, because the assignment is actually quite easy, right? Once you get past, keep in mind, over the last several assignments, the things that you're struggling with, they have to do with breaking the kind of the binds of what you think a language naturally offers versus what our language currently offers, right? We've never programmed in a programming language that didn't innately have Boolean expressions, right? Remember in your CSC470 class, we say, what's a Boolean expression? You say any expression that boils down to a single value of true or false. Trues and falses don't exist in our language. We don't have that, all right? So we need some way of representing ideas in our language. All right, so this kind of goes back, if we roll back the clock to the very early days of programming, I only go back as far as, let's say, C, just because that keeps us current enough that we can see where our languages came from. If you're a C programmer, there actually is not a Boolean data type. The Boolean data type does not exist in the C language. It's implemented as an int. All right, so C Booleans, you can find in a modern C compiler, you can find what's called a macro for bool, all caps. That'll be true and false. But it's not an embedded data type. So C Booleans, they've decided that true is represented as a 1. I'll say as a numeric 1. Now the good news for us is our language does support numbers, right? We got that one. In fact, that's all it supports. All right, so far we can be compatible with this. So true is represented as the numeric 1 in the old C language. False is represented as what?
Anything but 1.
Yeah, officially it's any number other than 1. Historically, it's viewed as 0. 0 is false, 1 is true, but the official,
Word on the street.
more than word on the street, the official implementation of C in the early days was that true is 1, false is other than 1, not 1. Yeah.
Wasn't it the other way around where false is always 0 and true is anything not 0?
I don't think so.
So I would say if 7 and it would trigger true.
It's possibly that is correct, but that's not how I recall it. It's certainly one or the other, but I thought true was always 1 and false was anything other than that. But actually what you're saying, where false is always 0 and anything non-zero is true, actually maybe makes more sense if I'm the language designer.
Mm-hmm.
Go ahead.
I just not a 0 or a 1. So were we supposed to make that a true or a false if it's?
It doesn't matter. I mean, this is your language. Think about this last assignment, how this last assignment deviated. Now we're going, so I started off giving you very structured. This is exactly how it works. Now we're saying, make your language support asking questions. Whatever that means for your language. Your language is your own little funky thing. All right? It should support asking questions in some sort of reasonable way. So did you find it?
According to the University of Illinois at Chicago, for interpretation, 0 is interpreted as false, and anything non-zero is interpreted as true.
Okay. That sounds more right to me anyway, so let's just update this. So true is represented as non-zero. False is represented as 1.
0.
Oh, I'm sorry. Sorry. Thank you. False is represented as 0. True is represented as anything that's not 0. Yeah, that sounds more correct. But in any case, the slide is still accurate from the idea of we have created a numeric representation for how do we want to deal with the idea of true and false. Make sense? Where most of us came up through Python and Java and things like that that have Boolean types built in. We didn't care how it was implemented under the hood. We just say true or we say false. If you did an Objective-C, it's yes or no. So Objective-C, instead of true, it's yes. Instead of false, it's no. But we don't have that in our language, so we have to come up with our version of this representation. So one possible thing we can do is we can model this like C and say, you know what? We're going to go ahead and say that true is anything but 0 and false is exactly 0. Right? And that would be reasonable enough. So we'll come into our code here, and we're going to build a constructor for a question. Somebody else asked a question online. I want to talk about this for a few minutes as well. I want to just address some of the questions that have come in just because they didn't necessarily make their way onto public Slack. Why constructors and predicates? All right, so if we look at our language here, our syntax, well, our implementation. So when I look at apply expression, this is really our implementation in here, right? Okay, we are using things from the scheme language to implement the functionality of the language we're inventing. That is different than saying the language that we're inventing already has all of the things that scheme supports built into it. There are situations like I think we ran into last class where we were passing, well, you just passed a number to it instead of a lit expression. Well, it just so happens that lit expressions boil down to numbers in our language. Make sense? Our language doesn't technically support you passing just a number. It wants you to pass a lit expression, which would boil down to a number. That makes sense? So there's this line between what does scheme innately support, and that's what we have available to us for implementing the logic of our language. But we still have to decide what does our language actually officially support. Because sometimes you're going to be able to get the right output because scheme is going to do its thing, right? Scheme is going to take something that looks like a number and say, this is a number, just like a lit expression would have done. All right, but scheme supports trues and falses already. Our language does not. So it would not be appropriate for us to ask if the first thing is true. Because true is not a thing in our language. It is a thing in scheme, but it's not a thing in our language. Could we add it to our language? Sure, we can adapt our language to now support an additional data type. That is a Boolean expression. That would be reasonable enough, right? But for right now, we are Gonna do this in this 0 or 1 way since we already have numerics. Go ahead.
I guess this is just building on top of that thing where it's hard to determine what's what between the two.
Mm-hmm.
Like, if that's the case, then can we use the things that are built into Scheme like EQV that, that's saying, is this equal? Or do we have to build something that looks
No,
see it?
you can use that for your implementation, to implement your language. That isn't something that your language doesn't support an EQV expression. So you can't write something in your language, your syntax. Our syntax for our language just naturally looks a lot like Scheme because we spent most of this semester thinking like a Scheme programmer, right? And because of that, we've tended to model our programming language to look like Scheme. Nothing requires us to do that. So for instance, you see me deviating from that a little bit. Scheme doesn't have something called a question. Scheme has something called an if, right? So I'm calling our version of an if a question because the way I teach programming is we remember things. So when we create variables, I'm going to call it memory. Asking questions, repetition. All right, so many languages do have a repeat statement, but it's not a common thing. Usually we think of it as like a for loop or a while loop, something like that. All right, so understand that just out of convenience, we have happened to choose a syntax for our language that allows us to mimic Scheme. Nothing would have prevented us from creating functions instead of a lambda, where you have a function that takes in a parameter list and then has a body. And maybe its name is func instead of lambda. It's a func expression. Does that make sense? We decided as the language inventors here to go ahead and choose to call that lambda to reinforce the idea that we've recently been bombarded with this idea of unnamed expressions, or unnamed functions rather, called lambdas. Does that make some sense? So in our mind, we want to differentiate between Scheme being a full-featured, already has a bunch of crap in it language, and what we are creating. What currently governs what our language supports?
The constructors we build for it?
Okay, that is that is evidence of the governing body, but what comes before that? What actually governs what constructors we should build? My grammar. So back here, we have the official grammar for our language. Okay, remember, we first built the slide, I would have said something along the lines of, Java can be described with a grammar. It'll be a lot bigger than this, a lot scarier than this, but Java can be described with a grammar. This is the grammar that currently defines our language. That makes sense? This is all our language can do. Anything that's not in there is not legal syntax in our language, even if Scheme already supports that data type. There's a very good chance Scheme's going to already support most of the stuff we do in here because it's a programming language. So we can start differentiating ourselves from Scheme by calling things different names, right? But this is our language. All right, that makes some sense? So we're going to add something to our grammar. What's each of these lines called? So as a whole, our language is defined by a grammar, and our grammar is a collection of what? Productions. So this is a production, this is a production, this is a production, this is a production, this is a production. A grammar is a collection of productions. So every production is a rule in our grammar. That makes sense? This guy right here is meant to unambiguously describe our language, even though sometimes it can be a bit ambiguous, as in a lambda expression is a lambda, an app expression is a list containing 2 LC expressions. Well, actually, one or more LC expressions, where we have said this first one must be a lambda. That's like a caveat we have insisted upon, because we only can implement our app expression, or we can say the way our app expression is implemented assumes that this first LC expression, which by legal syntax can be any LC expression. That's what my grammar says. My grammar says that an app expression, that particular production, says an app expression is a list whose first element is an LC expression and will have 0 or more additional LC expressions. So there's nothing that grammatically, syntactically keeps me from writing a lit expression as my first element of an app expression. What we're saying is, as the implementers, a lit expression won't cut it. Even though I've told you that grammatically you could pass it a lit expression, that's technically an LC expression, I am expecting you to give me the production that is a lambda expression, because that's the guy I'm going to pass these parameters to. Go ahead.
What's the reasoning for leaving that, I guess, looseness or flexibility there?
Because we don't have a way of expressing specifically a lambda expression.
Okay.
We have an LC expression grammar. We could say lambda expression here in our, so let's say officially using a formal language like this, we would not have access to our internal productions.
Okay.
So we would have access to a top level grammar. So our stuff here is made up. So like, for instance, somewhere else there's a grammar called a symbol. Somewhere else there is a grammar called a number. That makes sense? So we're able to say that a lit expression follows the grammar of anything that's a number. A var expression follows the grammar of anything that's a symbol. A lambda expression follows the grammar of a list containing the word lambda, specifically a list containing 0 or more symbol, technically it would be symbol, but I said symbols, and then anything that meets this grammar. So officially, I really can't say much more than LC expression here, even though a human being reading this, we could throw lambda exp inside of this first part and probably get away with it just fine, because who's reading this is a human being, right? They would say, okay, that's a lambda. That's what I'll give it. Go ahead.
Is there a way for us to enforce the grammars? I mean, I can say, like, if we're, like right now, app expression takes 2 language calculus expressions, but, I mean.
Can we error check it?
We can throw whatever we want in there, so.
Yeah, I mean, that's at the implementation level.
Yeah.
So this is at our description of the language level. This is the plan, right?
Yeah.
This is our blueprint from our language. Our language, we support all these productions. Now in our implementation, we've decided as human beings that this app expression, this first thing here, must be a lambda expression, not just any old lambda calculus expression. So with that in mind, in our implementation, we could check against that and say, if the car of the thing is not a lambda expression, test the predicate, right? Mm-hmm. Then scream and yell that this is not a executable app expression. I don't know what to do with this kind of crap. Mm-hmm. But that would be it at the implementation level. That make sense? So we have the language design here. Then we go and implement. So look at this grammar. Everybody's committed this to memory. Look at this grammar. Now we'll go over to our implementation. And what do we see in apply expression? The implementation of that grammar. We have a lit expression, a var expression, a lambda expression, a repeat expression, our Blaine style repeat expression, and then our else, which is our app expression. All right, so we can even put a little, this is an app exp. So, as Austin pointed out, if we wanted to enforce, error check this, in our app expression here, we could say, if you didn't give me a operator that is a lambda, I'm not doing anything else. I'm going to print out an error message and say, do it right next time and try it again. We didn't do that because we don't error check, because our language requires you to be a perfect programmer. Does that make sense?
Yeah.
Okay, go ahead.
The other thing was, I know we're all pretty familiar with like typing types. I know we've only really done anything with integers. Is there a way for us to do stuff with like doubles or decimal numbers in this? Like, at least how to start implementing that, or?
Well, we are going to.
Okay.
We're going to implement a grammar of types.
Oh, really?
Yeah.
Sweet.
Yeah, we're just getting started. Yeah, we're just getting started here. But until we can't go that deep until I get you to wrap your mind around what we're doing, because it's really abstract, right? And we're having so much trouble, it seems like, separating between the full-featured programming language that somebody else invented and our crap language that's currently under development, right? We're that building that still has the plastic all around it and stuff like that, and it's not done. Okay, this department is not move-in ready. It can do a couple of things. I mean, if you had to sleep in the corner of this place, you could. Okay, but it is not. God forbid if you have to go to the bathroom, you're gonna have to pick a neutral corner. Right? All right, plumbing is not in yet.
Windows.
Take a gap in the plastic.
You can go pee out in the forest.
How do you know this is anywhere near a forest? Is that in your grammar? V? Does your grammar support the language is near a forest? I guess your homework is to make it near a forest. I'll have to think about this before next class and figure out what does that mean. All right. So does this make more sense about the differentiating factor? Our grammar just happens to look a lot like Scheme right now because we're in that mode. Now I'm starting to kind of push you a little bit towards inventing your own things. If you wanted your question expression to be some random set of keys, LOL question mark or something like that, and that's the syntax of your language for, if you want to ask a question, you use lol question mark. That's okay. It's your language. Right? Maybe it's not all that intuitive, but it's fine.
Scheme support
I honestly don't know. But I mean, an emoji is just a colon followed by something is just a code, right? I mean, that question, I know you're trying to be funny, but that question is very related to how we started this idea today. How do we represent things that aren't already included? How are emojis actually represented? We put a colon followed by some stuff, and then the system interprets that representation and associates it with some picture. That's what an emoji is, right? How do characters work in our modern programming languages? We have a number, and that number is marked as type char, which says when I use that guy, I need to go look up that number on some chart, the Unicode chart, and map it to the character that he actually means. It's like emojis. We have the emoji for A and the emoji for B and the emoji for C. Does that make sense? These all have to do with data representation because computers are all about the number. So is our baby language right now. All we have is numbers, right? Starting to make some sense? Our language doesn't do that much yet. Okay, so we are going to, I was starting to talk about this. So why these constructors and predicates? What's the purpose of these? So in this context of we have this grammar for our language, which formally defines what our language is capable of. And then we have the Scheme programming language, which is the tool we have chosen. This is the tool we have chosen to build our language out of. Okay? Where do these constructors and predicates come in?
Aren't we essentially just defining keywords that actually make valid programs of our language?
Do we have to have constructors and predicates? Could we omit them completely and still build a language?
A simple language.
Any language. What are my constructors? Aren't my constructors all just lambdas? Does anything prevent me from just writing those lambdas inside my implementation instead of having a constructor that does it for me? In a complex language, things are going to start getting pretty ugly pretty quickly, right? Okay. What do the constructors and predicates let us do?
Simplify things.
Simplify things so that when we look at our implementation, it looks like our grammar. Here's a predicate that says, am I looking at a lit expression? We know under the hood, there's a lambda behind that that's asking the question of whether that dude is a number. Nothing prevents me from putting number question mark there. But by me writing it like that and using the predicate that I custom made, I'm able to ask a question that at a glance says, this looks like the grammar. It's a convenience for us so that we can focus on the implementation of the language rather than the question of which kind of expression am I looking at. We don't have to have these predicates. That would just look weirder. This would look weirder. This would look a lot weirder. These first two wouldn't, they wouldn't be any longer really. This would be number question mark and this would be symbol question mark, right? So this is just as good. But you start getting down to a lambda expression, now you're looking whether the car of the thing is equal to a lambda, and then if you're not error checking, then you're just kind of hoping that the rest of it's cool. If you really wanted to be discreet about it, you would say, is the car a lambda? Is the catter a list? Is the cadder a lambda calculus expression? And then you have to decide, well, what's a lambda calculus expression? It's any one of the things that's in my grammar. Okay, that gets sketch quick, right? If we're going to do a whole bunch of error checking. We're kind of getting the point here. These predicates allow us to quickly, we know there's implementation up above in our code where these guys have logic in them. But at a glance here, we are looking at the implementation of our grammar. And it looks a lot like our grammar. This allows us to connect those two things together. So these constructors and these predicates have absolutely nothing to do with whether we can successfully create a language. It's a convenience for us to be able to build something that is one of these expressions, and probably more importantly, for us to have a predicate that's compatible with each constructor that allows us to ask, is the thing I'm currently looking at one of those guys? So that our implementation here looks like our grammar. That makes sense? Okay. Super important, the stuff we've talked about so far. Because between last class and this class, and really the last two classes, it's become apparent to me that we're having problems differentiating what our different pieces mean.
I feel like I understand it better now.
All right, so that's my goal. So I want everybody, it's not embarrassing to say I still don't get it. That's okay. We could try to hit this from a different angle, but I want you to understand that these pieces are separate pieces. And this guy here, that's what our language can do. That is all our language can currently do. This guy here is the implementation of that grammar. In terms of all of these constructors and predicates that we built up here that allow us to conveniently say, am I looking at a lit expression, which just says, is the guy a number? Am I looking at a var expression? Am I looking at a var expression? Is the guy a symbol? So on and so forth. Make sense? This makes it cleaner when we look at our implementation for apply expression. All right, so questions about any of that?
So, constructor is mostly like a list, right?
Well, it doesn't have to be. Here's a constructor for a lit expression. What does it do? It takes in a number and just spits out the number. We could look at that and say, well, why are we wasting our time? But if down the road we decide to change the way we're implementing lit expressions. We can say, well, now a lit expression is maybe it builds a list whose first thing is the symbol lit and whose second element is the number, right? And then lit expression's predicate would then change to see, is the car lit and is the catter a number to detect it. So these two guys work hand in hand. This guy needs to test if what I'm looking at meets that guy.
Oh, I have a question then. So then the constructor cannot make a recursive call, right?
The constructor, well, so she asked this for the Ann Arbor people. She asked if the constructor can be a recursive call. The constructor can be whatever it needs to be to construct an expression of that type. The one thing you want to not do is, and again, this is part of what we're trying to clarify for today, is you don't want to mix your constructors and predicates with your implementation. A constructor is meant to build the right structure. You would construct a window, and then you would take that constructed window and you would go and install it into a house. Make sense? You wouldn't construct a window and install it all at the same time. All right, because now that's less usable. Because if you already have a window, now the only way you can get that window installed is by constructing a new window and installing it. Make sense? So we want constructors to build a structure, and then our implementation uses that structure. So when you're asking the question, can you have recursive stuff inside of your constructors? The answer would be technically yes if it made sense. But what you want to avoid is the mindset you want to be in is that your constructors are not part of the implementation of your language. They are a way of us representing what our language looks like, not how it works. Yeah.
So to clarify that, we use constructors in Scheme for creating our language, but our language itself does not yet support constructors?
Oh yeah, because that's definitely true.
Yeah,
but let's say that's true. But the constructor you're talking about is constructors for like object-oriented languages, right?
Yeah.
This isn't even that.
Right.
So we're calling both of them constructors, but when we start implementing object-orientedness into our languages, now we're starting to support fields and methods and constructors and collections of constructors. Well, we're actually not as far off as you might think. Object-orientedness is not hard. That's the whole point of this class, is to, in the end, after we get past all this intimidating stuff, is realize that languages are not overly complicated. They're really not. Okay? But our brains are so focused. We started off in computer science not even knowing what programming was. Then we trained you how to program on a tool that already is a programming language. And now I'm wanting you to separate that knowledge and saying, this is what you expect programming to be. What if I asked you to build your own tool for a language and you were handcuffed? You can only do this stuff, these 2 or 3 or 4 or 5 things. You can't create objects yet. You can't even represent Booleans. Okay? You don't know what chars are. We got numbers, that's it. You need more than numbers? Make your language better. Right? But we just can't do that yet. So what you're really asking is, the use of constructor in your question is different than the use of my constructor here.
Yeah.
My use of constructor here is saying convenience function for letting us for us to have the proper syntax when we're building expressions in our language. Where constructor in his context is
I was thinking about it differently.
build objects. Yeah. They still construct stuff. So ultimately they're doing a job of constructing. But this is a convenience for us to go down and write an expression in our language like this. We wrote that expression in terms of the constructors rather than in terms of the direct syntax. That make sense?
So that means we don't have to define our language yet, right?
Well, we have. Our language is defined here. And we built constructors and predicates for each of these for convenience. And then we implemented our language here. That's our current implementation for that guy. Go ahead.
Remind me once more how within our language we assign a variable expression to a other expression.
We can't. So in our language right here, this is how we do it. We give it a pre-cooked environment. Yeah, if you want to have a variable c equal to 3, when you apply your program, you give it an environment that already has c bound to 3. Because we don't have the ability to define variables yet. We have the ability to bind a value to a variable in an app expression.
Okay, that's what I was
Okay, but if we want to have variables that we can look up, var expressions don't work in our language off the cuff before we've done an app expression unless we've pre-baked it into our environment we passed in, as if that number is coming from someplace else. That makes some sense? All right, so what we'll start off with next time is we're going to follow these steps. I know you already had this for your assignment, and that's a done deal, but does everybody feel better about all the pieces we're dealing with here? Okay, so we'll write our grammar here, because we're out of time now. We'll write our grammar here for what a question expression looks like, and then we'll implement it. So no homework for Friday, but tonight we have a tech talk, and by midnight tomorrow you have a midterm exam you have to submit. Those are your homework assignments, okay? So remember, the exam takes, I think I'd give you like 2 hours or something on it, so you won't see a timer. But show me what you're capable of on the exam. The exams aren't meant, my exams aren't meant to be a time thing. You know, the idea is if you sat in front of it for 14 hours, you're probably not going to do any better on it than you would if you sat in front of her for an hour. Show me what you can do. Normal rules. If you do better in the final, I'll replace your midterm exam score with it. 10 questions, your normal stuff. It's over the stuff we've talked about so far in this class. Exam's pretty fair. It'll give you a little litmus test of where you are. And then we'll kind of go from there. I'll have the exams all graded by the end of the day on Friday, because that's when I have to have midterm grades in. That's kind of why I threw the exam. That's why I made them online, and that's why they kind of were almost a last-minute addition. Usually, I don't have to have midterm grades in until the Tuesday following fall break.
Yeah.
And for some reason, we're earlier this year. I don't know. It's possible because we have a new registrar, and maybe that's just the way she wanted it. But in any case, I made the exams as soon as I got the email about when I had to have midterm grades in. All right. I will see everybody on Friday. Well, I'll hopefully see all of you tonight at the Tech Talk. All right.
Oh, question.